So this is the 31st session on relative velocity. So in this session we will discuss the relative velocity shortest distance problem between two moving points. Okay. So I'll take up some problems. Okay, fine. So we discuss the relative velocity shortest distance problems. So we discuss that relative velocity shortest distance problem. Shortest distance problem for two moving points. So I'll take up some questions to demonstrate the concept. Okay. So I take the first question. Okay. So I write down the question here and then I'll discuss it. Okay. So problem is this: S1 and S2 are two moving ships. S1 and S2 are two moving ships, and initial separation between the ships is L, and ship S2 is south of S1. S1 is moving at a constant speed v with respect to ground towards south. At a constant speed v with respect to ground, G for ground, towards south. So the V was left out. So ship S1 moves at a constant speed v with respect to ground towards south, and ship S2 moves eastward at constant speed v with respect to ground. Fine. Two things we have to find. First we have to find this, the shortest distance between these two ships in course of their motion. Shortest distance between the ships in course of their motion. And second, the time after which the distance between the two ships becomes minimum. Time after which the distance between two ships becomes minimum. Okay, fine. So this problem will solve by two different methods. By two methods we'll solve this problem. Solved by two methods. First method is method of calculus using conventional method. Maximum minima concept. When y is a function of x, y is minimum, dy by dx is 0. That two concept we'll use. Okay. So conventional method, that is the first method. Which is the conventional method. And second is using the relative velocity concept. Okay. Second method is using the concept of relative velocity. So by two methods we'll solve this problem. Fine. So I'll rub this. Okay. First I'll solve it by method 1, calculus method. So we solve this by method 1. I just now stated using the method of calculus. So we draw the initial situation. So this in method 1 we are solving the problem as seen from ground frame. So what we'll do, first we draw the initial diagram, okay? This is S1 and this is S2 at time 0. S2 is due south of S1. This is the top view from up we are seeing, okay? L is the distance between these two ships. Ship S1 is moving down south at a constant speed v with respect to ground. S2 is moving towards east at a constant speed v with respect to ground. So now what we do, we set up a convenient coordinate system. We take a coordinate system whose origin coincides with the initial location of S2. So this point we take origin. This is the x-axis eastward direction and y-axis along northern direction. So initial coordinate of S1 is 0, L and initial coordinate of S2 is 0, 0. But the coordinate system is fixed to the ground, not to the ship. Okay. So even the ships move, the coordinate system stays fixed there as seen from ground. Now this is the situation at time 0. Okay. What we do at time t, we write down the coordinate of these two ships. So at time t, this is the location at time 0 and this is the location of S2 at time 0. At some time t, S1 must have reached here and S2 must have reached here. Diagram is not drawn to scale, okay? In t time, S2 will move a distance Vt rightward. So at time t, coordinate of S2 will be Vt, 0. Similarly, in t time, S1 will move a distance Vt towards south. So at time t, coordinate of S1 will be 0, L minus Vt. I am repeating again, the diagram has not been drawn to scale, okay? So now at time t, S2 is here, S1 is here at time t. This is S2 at S1 at time t. So at time t, this is the distance r between these two ships. Okay. Now r can be found using the Pythagoras theorem. This is Vt, this is L minus Vt, and this is Vt. R from Pythagoras theorem, r is just equal to Vt whole square plus L minus Vt whole square. This is going to be the value of r. That means r is equal to Vt whole square plus L minus Vt ka whole square. Alright. So when r is minimum, implies that r square is also what? Minimum. That means from the rule of calculus, d by dt of r square is 0. That means d by dt of r square, write this expression here. V square t square plus L minus Vt whole square is 0. This means d by dt of v square t square 2v square t. This means 2 times, we differentiate using the chain rule of calculus. I hope that is familiar. L minus Vt into minus v. That is just equal to 0. So 2v goes away, as you can see. Only we are left with Vt. Minus L plus Vt barabar 0. So 2Vt barabar L. T barabar L by 2v. This is the first answer. Distance between the two ships becomes minimum after this much time, L by 2v. Now we also have to find the minimum value of r. For this what we do, we write the value of V2 in this. So Vt is just equal to L by 2. R minimum, we substitute the value of Vt in the expression for r square. So yeah, in this expression. R min is just equal to Vt whole square plus L minus Vt whole square. Vt is just L by 2. L by 2 whole square plus L minus L by 2 whole square. That becomes L square by 4 plus L square by 4. This is just L square by 2. L by root 2. This is the answer, okay? So method 1 has been fully solved. So shortest distance between the two ships in course of their motion is L by root 2. And after time L by 2v, the distance between the two ships becomes minimum. This was the conventional solution in the ground frame. Fine. This was the conventional solution in ground frame. So t is equal to L by 2v. After this much time, distance will be minimum. And minimum distance between the two ships will be L by root 2. Alright, fine. So So this is method 1, which is fully discussed. This is just a conventional method, okay? Now we solve the same problem by method 2. Fine. So method 2. Using the relative velocity concept. Using the relative velocity concept. First of all, what we do? We determine the relative acceleration between these two ships in ground frame. So AS2 S1G, that is the relative acceleration of ship S2 with respect to S1 in ground frame, that is just equal to acceleration of S2 with respect to ground A2G minus acceleration of S1 with respect to ground, that is A1G. Now with respect to ground, ship S2 moves along a straight line eastward direction at a constant speed v. That meaning velocity of ship S2 with respect to ground is constant in magnitude and direction both, and therefore A2G becomes 0. And similarly S1 moves at a constant speed v along a straight line towards south. So velocity of S1 with respect to ground is also constant v south. So A1G जो है that also becomes 0. So 0 minus 0 is 0. So that means AS2 S1G is equal to 0 for all times. So this means that relative acceleration between these two ships is 0 for all times. But it is known that relative acceleration between the two ships in ground frame is just the derivative of relative velocity, v relative, in ground frame, where v relative is the relative velocity between the two ships at time t. But since this quantity is 0, this quantity is 0, this quantity is just equal to this. dv relative by dt in ground frame is equal to as2 s1g. Since this is 0 for all times, that means this is equal to 0. Yani ki d by dt of v relative is 0. That means v relative is constant. Relative velocity between the two ships is constant. This means that if you observe s2 from s1, then s1 will observe that s2 is moving along a straight line at a constant velocity. Or if you observe s1 from s2, then s2 will observe that s1 is moving along a straight line with constant velocity. So we can take either of them. Suppose we solve the problem as seen from s1. Alright. So this will mean that s1 will observe that s2 moves along a straight line at a constant relative velocity. So we are solving it in the frame of s1. Fine. So s1 will observe that S2 moves along a straight line at constant relative speed u relative say. Now what we do next, we have to find the u relative. U relative is the constant relative speed between the two ships. Now, if a particular quantity is constant, what does that mean? That quantity doesn't change with time. Okay. So, since relative velocity is constant, then constant relative velocity must have the same value as it was at time 0. So, what we do, we find the relative velocity between these two ships at time 0, and that will also be the relative velocity between these two ships at any other instant because it is constant. Fine. So what we do is, first we find the initial relative velocity of S2 with respect to S1, and that will also be the relative velocity between these two ships at any other time instant because it is constant. So I rub this, okay. As I mentioned just now, I am solving the problem as seen from frame S1, in the frame of S1, okay. So we find the initial relative velocity of S2 with respect to S1. So U relative is the initial relative velocity of S2 with respect to S1. That is US2 S1G. That is equal to U2G minus U1G. That is just equal to U2G and reverse of U1G. Now this is S1, okay. This is S2. U2G is nothing but V rightward, eastward direction, top view. And U1G is V southward. So minus U1G is V northward. This is V minus U1G. This is U2G. So U relative is the vector sum of these two, and the vector sum of these two. That is, we complete the parallelogram law using these two adjacent sides. This is the U relative, see. And it can be seen, this is V, this is also V, this is also V, this is V, this is also V, this is V, right angle triangle. U relative becomes V and V, Pythagoras theorem. V root 2, fine. So, at time 0, S1 is here, S2 is here, S2 is moving at a constant relative velocity of V root 2 along the bisector of these two because they are equal. So this will bisect. From geometry it is seen. This is theta. This is also 90 minus theta. Tan theta is equal to V by V. Tan theta is just equal to V by V. That is 1. Theta is just equal to 45 degree. So 90 minus theta, that is also 45 degree. So at time 0, this is the situation. S1 is here, S2 is here. S2 is moving at a speed of V root 2 along the bisector of these two in along northeast direction. Okay. Now we are solving the problem as seen from S1. As seen from S1, S1 is at rest. S1 won't move because with respect to itself it is at rest. Only S2 will continue to move with the same velocity. So at time 0, S1 is here, S2 is here. At all subsequent instants also S1 will remain at its same location. Only S2 will be moving along this line. So S1 will observe that S2 is moving along this straight line bisector northeast direction at a constant speed of V root 2. Okay. So with respect to S1, S2 is moving along northeastern direction at a constant speed of V root 2. Now what is the shortest distance between these two ships? The shortest distance between these two ships is just the perpendicular distance let fall from S1 on the line of motion of S2. So we should drop the normal here like this. This is the shortest distance, R minimum, between the two ships in course of their motion. Now this quantity is how much? This quantity is given to be L initially. This is also 45 degree. This is also right angle. This is a right angle triangle. This hypotenuse. This is the one of the sides. R min by L equal to sine of 45 degree. 90 minus theta is also 45 because theta is 45. So what do we say here? R minimum by L equal to sine of 45 degree. Yani 1 by root 2. So R minimum becomes L by root 2. This is one answer. This is the same answer as we obtained using the conventional calculus method. And this we have solved using the relative velocity concept. So shortest distance between the two ships in course of their motion is L by root 2. Fine. Now we have to determine after what time the distance between the two ships will be minimum. So time after which initially S1 is here, S2 is here. S1 is always at same location as seen from itself. Only S2 continues to move along this direction. Short distance between two ships is minimum when S2 is here at this location. S1 is at same location. So time after which the distance between two ships become minimum is same as the time in which S2 moves from here to here. Okay. So time taken will be distance moved from here to here, this distance. Let's call this distance as say S. The time will be this distance divided by relative speed of S2 with respect to S1, just equal to V root 2. Time equal to distance by speed. When the relative speed is constant, then time taken is distance covered by time by speed. The distance covered is s, and relative speed of s2 with respect to s1 is v root 2. How s will be found how much? This is L, this is 45 degree, this is S, right angle triangle, this is right angle here, this is the base, this is the hypotenuse. So S by L equal to cos of 45 degree, 1 by root 2, okay. S becomes L by root 2, fine. S becomes how much? L by root 2. This value of S we substitute here. S L by root 2 into what? V root 2. L by 2V. This is the required time C. This also is the same answer as we obtained using method 1. Fine. So shortest distance between the two ships in course of their motion is L by root 2, and time after which the distance becomes minimum is L by 2V. Okay. So this problem has been solved by both the methods. By both the methods, the given problem has been fully solved. So R minimum is just equal to L by root 2, and time after which distance will be minimum is equal to L by 2V. Alright, is it clear? So this one problem I have discussed, okay. I'll take up one more question on relative velocity. This is similar to this problem, only I'll change the data, okay. Only with the difference that S2 is moving towards east, not at speed v but say at 2v. Remaining all the data is the same. Now I'll rub this, okay, fine. So we take one more problem in this second session, okay? Example 2. Example 2 is again similar to previous question, with the only difference that S2 is moving at a constant speed 2v with respect to ground, not v but 2v. Everything is same as in previous question. I'll not repeat the entire question again, okay? And I just write down the difference, okay? Example 2 same as in previous example, with the only difference that S2 moves eastward at a constant speed to v with respect to ground, okay. S2 moves eastward at a constant speed 2v with respect to ground. The remaining data is everything is same. Okay. Again, we solve this not by conventional method but by relative velocity method. Solved by relative velocity method. So again, A relative will be 0 as it was because ship velocities of both the ships are constant. So I'll just repeat that calculation. A relative, it is the relative acceleration of S2 with respect to S1 in ground frame. That is just A2g minus A1g. Acceleration of S2 with respect to ground is 0. It is moving eastward at straight line at a constant speed 2v. A1g acceleration of ship S1 with respect to ground, that is also 0. It is moving along southern direction straight line with respect to ground at a constant speed v. This is 0. So both are 0. Difference is also 0 for all times. So this means A relative is 0 for all times. This means relative velocity between the two ships S2 and S1 is what? Constant at all times. And that is just equal to the relative velocity at any time instant. It's just the relative velocity at time 0, which is u relative, as it was in the first example of this video. Okay. So A relative is 0 for all times, V relative is constant for all times, V relative is equal to u relative. U relative is the initial relative velocity between the two ships. U relative is the initial relative velocity between the two ships. That is also the relative velocity between two ships at any subsequent instant also. Now what we do, we find this U relative again. U relative is the relative acceleration of S2 with respect to S1 in ground frame. That we write as U2g minus U1g. that will be written as u2g plus reverse of u1g. Now u2g is what? 2v rightward, eastward. u1g is what? v southward. Minus u1g is v northward. Reverse and add concept. So this is the C. This is S1. So I write in this way. See, I write here. Okay. So this is S1. This is S2. We have to find U relative. U relative has to be found out. U relative meaning what? U relative is this U2G is what? 2V rightward. Vector sum of these two vectors. Parallelogram method of vector addition. Tails coincide. Tails of both the vectors are made coincident with parallel shifting. U2G is 2V rightward. U1G is V south minus U1G is V north. Tails of these two vectors are made coincident by parallel shifting. This is minus U1G V south north, 2V rightward, U2G. Vector sum of these two. With these two as adjacent sides, we complete the parallelogram rectangle in this case. This is the U relative. This is also the relative velocity at any other instant also. And you can see that U relative is just the right angle triangle. V, this is also V. This is 2V. This is Pythagoras theorem. This is how much? V square plus 4V square. So U relative is equal to V root 5. This is the relative speed, okay? So let's call this angle as theta. So this angle becomes how much? 90 minus theta. Alright? So how to find this theta? So this is the right angle triangle. This is equal to V. This is equal to 2V. Tan theta equal to V by 2V. Alright? Tan theta is equal to V by 2V, that is half. Okay? So initial relative velocity is V root 5 along this direction. But that is also the relative velocity at any other instant because relative velocity is constant. So as seen from S1, S2 will move along a straight line at a constant speed of how much? V root 5 at an angle of theta with the eastern direction, where tan theta is how much? Tan theta is just equal to how much? Tan theta is half. Now shortest distance from between these two ships. Now problem is being solved from S1. With respect to S1, S1 is at rest. So S1 will stay there always. S2 will moving along this line. The shortest distance will be the perpendicular distance from S1 on this line of motion of relative motion of S2 with respect to S1. So this is going to be the R minimum. This is the minimum distance between the two ships in course of their motion. Now this distance is how much? This distance given to be L. Fine. So this is theta. This is 90 minus theta. R min by L equal to sin 90 minus theta. Right angle triangle. This is the hypotenuse. These are two sides. So what we write here? R minimum by L equal to sin of 90 minus theta. That is equal to cos theta. So R minimum is equal to L cos theta. But tan theta is half. Tan theta is half, that meaning from trigonometry cos theta will be 2 by root 5. We substitute cos theta here. R minimum is L times 2 by root 5. 12 by root 5. That is R minimum. First answer has been fully obtained. Okay. So first answer has been obtained. R minimum is just equal to 12 by root 5. This is the shortest distance between the two ships in course of their motion. Fine. Now we also have to find the time after which the distance is minimum. So when S2 comes here, then the distance between the two ships is minimum. Initially S2 was here, initially S2 again, S2 comes here when separation becomes minimum. The time after which the distance between two ships becomes minimum is the time after which S2 moves from here to here as seen from S1 with a constant speed of V root 2, V root 5. And it covers a distance of this much distance S. So time taken will be distance from here to here. Let's call this as S. Divided by constant speed U relative, that is just equal to V root 5. How to find S? Tell me. S is this is S, this is S, this is L. S by L is just cos 90 minus theta. I'll write it here. S by L is cos 90 minus theta in sin theta. In S is equal to L sin theta. Okay. S is just equal to how much? L sin theta. We substitute L sin theta here. L by V root 5 sin theta. Okay. Sin theta will be here, sorry. Sin theta will be here. Now tan theta is how much? 1 by 2. Sin theta will be 1 by root 5. You substitute 1 by root 5 here. L by V root 5 into 1 by root 5. That is L by 5V. This is the answer. So the second part of the question. So distance between the two shapes will be minimum after time L by 5v. After time L by 5v, the distance between the two shapes will be minimum in course of the motion. And minimum distance between two shapes in course of the motion will be 2L by root 5. Okay, fine. So this 31st session on relative velocity, two problems on shortest distance problem have been taken up. Achha, I'll tell one more thing, I'll just repeat. See, this method is going to be useful only when this relative velocity concept method for finding minimum distance, that is useful only when the relative acceleration between two moving bodies is 0. So that relative motion is along straight line. If relative velocity acceleration is non-zero, then the motion will not be in general on straight line but some curved path. Then this method is not of any much use. It's better you solve it by the calculus method only. So this method of relative velocity to find shortest distance is useful only when the relative acceleration between two moving points is 0. So that relative velocity between two moving points is constant. So that as seen from one point, other point moves along a straight line at a constant relative speed. So then it is useful. But if A relative is non-zero, then in general relative velocity will not be constant. It will vary with time, either in magnitude or direction or both. Since it will vary in direction also, it means relative motion will no longer be along a straight line but some curved path. So this method is then not very useful. Then you better solve it by calculus method only. But this method is especially useful when the relative acceleration between two moving bodies is 0. Then this method is alright. Very good method. Okay. So we close this here just now. In next session also I'll take up some more problems on shortest distance problem on relative velocity. Fine. I close it here. Okay. Fine.